Hi, everyone. I'm Tal Malkin. Welcome to this part of the lectures on theory of computation. I'm a professor at Columbia University in the theory group, as well as in the security group. I got interested in computer science in general, and specifically in theory of computer science, starting from math. I did my undergrad in Israel at Bar Ilan University, where I majored in math and computer science, but math was really the thing I was passionate about. And then I took a class on theory of computation, similar to this class you're taking now, and I really fell in love with computer science. I then did my master's at the Weizmann Institute of Science in Israel on temporal logic, and then I did my PhD at MIT on cryptography, which is my main area of research. I then worked a couple of years at AT&T Labs Research, and I've been at Columbia for over 15 years since then. So just to say a word about my area of cryptography, it's an area within theory of computation, and it's basically the mathematical foundations behind any applications requiring security or privacy. And it's strongly related to complexity theory. In general, both directions, both cryptography and complexity theory have got a lot of feedback from each other. Just to give a very simple example, currently what you're studying in the class is the limits of computation and what can and cannot be computed. The next part of the class you'll learn about complexity theory, which is basically what can or cannot be computed efficiently. Or possibly also considering other models of other resources like randomness, etc. So cryptography is very related to that because often we want to prove theorems of the form, no adversary that runs in a reasonable amount of time can break my scheme. So this is an immediate connection to complexity theory because we want to analyze what cannot be done efficiently. There are deeper connections, there are many connections between the two of them. And in fact, defining the primitives correctly in cryptography is very important as well. Okay, so let me give a brief overview of what I will cover in the next couple of lectures. So our topic is continuing the topic from before, which is basically about the limits of computation. It's about undecidable and or unrecognizable languages. So what you've already seen, and I'll recap briefly in the beginning of the lecture, you've seen that almost all languages are in fact not Turing machine recognizable, and this can be done by a simple counting argument. And you've also seen some specific examples of languages that are undecidable or unrecognizable, such as the halting problem. And this was done using the technique of diagonalization. Now you might think, although I would disagree, but you might think that these examples are not very natural because it involves a program running on its own code. But it turns out to be very essential. And starting from this point, we could in fact prove, and this will be my topic, we can in fact prove many, many other problems that are both important and natural, that it's obvious we would want to solve, are in fact not solvable. So either not decidable or not recognizable by any algorithm. Okay, so this is what we will cover. We will give several examples and general techniques. Main techniques we will cover will be reductions in general and the specific case of mapping reduction, which allows you to prove that some languages are not recognizable. And we'll talk about Rice's theorem, which is a very general theorem, which in some sense says that anything interesting about what a program computes, in fact, cannot be decided. We will talk more about that. So see you in the next lectures.